Now I want to turn your attention to the data analysis portion of this little write-up that I have for determining the density of the water in the lab. In the previous video we talked about what I expect to see on your papers for your data tables and your graphs. So I'm not going to go into those details now. What we're going to do now is just to really interpret your graph. Since this was a density of water lab activity, we want to see if we are actually able to determine that. So here I have a little opening statement under data analysis in my write-up. It says, the density of water is the mass divided by the volume. This can be determined graphically by finding the slope of the line of best fit. So when we look at our graph, we see that we've plotted mass and volume, and in fact mass over volume is density, and when you're calculating the slope of a line, you're going to be taking the rise over the run. You're going to be taking the mass and dividing it by the volume. So the slope of the line is actually the density of the water. And so I've written this out as an equation right down here. So slope is equal to rise over run. And in order to calculate the slope, I'm using this 2-point formula. And so these 2 points can come from any point along this line. You take one up here and you take one down here. And what I did was I said, well, these 2 points come pretty close to the line, so I'm just going to use those. That's this point in the data table here, and this point which is shown in the data table right here. So I took the values for those 2 points and I plugged them in. Now you could measure anywhere along this slope, but in this case I just plugged in the numbers for 2 of the masses and the 2 of the corresponding volumes. And when I did that, then I got a value of 1.02 grams per milliliter. Is that right or is that wrong? Well, it's pretty close. We know that the density of water by definition is 1 gram per milliliter. You could say it's 1.00000. It is exactly 1 gram per milliliter because that by definition is what it is. We got 1.02. Now how much different is our value than from the actual value? And so we can use a percent difference to calculate accuracy. So our experimental error is determined by calculating the percent difference between the experimental value and the actual value. So our experimental value is 1.02, and we're going to subtract that from the actual value, which is 1, take the absolute value of that and divide it by the actual value, multiply it times 100 to find that our experimental error was 2%. And that's pretty good for high school laboratory work. I think anything under 5 is great. Anything under 10, you might have to explain it. And up to 20. 20 is not really. 20 is a lot of experimental error. You should be able to do better than that. I'm looking for 5 or 10%.